What is going on, guys? Welcome back to another video. In today's video, I am going to show you how to implement your own linear congruential generator. Now, if you don't know what this linear congruential generator is, it's basically a random number generator. Very easy to implement and not truly random, as we all know with every single algorithmic generator, it's pseudo-random, but nevertheless, a pretty good algorithm to generate some random numbers for your game or whatever. Just don't use it for cryptographic hash functions because I guarantee you someone's going to crack that. This is very popular and using it for cryptographic things is very bad. There's way more complicated things we can use, and again, some of them even use the TPM hardware modules in your computer. That's why Windows 11 requires that. So again, you can use this for anything but storing your passwords or any other secure thing. So without further ado, let's get started. So first, I'm going to create a function that basically generates some random numbers stored in a array for us. So let's do that first. So the private slavic, we'll do some long numbers because integer numbers, if you, I'll show you later what I mean, but LCG, okay, let's get this out of the way. So int number of nums, this just specifies how many random numbers you want to generate here. Now we can do seed. We need a starting seed because if you're unaware of this LCG thing, it's basically a recursive sequence. Just like the Fibonacci sequence, you need to have a 0 and 1 to be the seed, and then you can start adding on numbers like 2, 5, 8, 2, 3, 5, 8, sorry, 13, 21, I think that is the sequence. But that you need 0 and 1 to start. And we need a long modulus, I would say. I mean, modulus can be an integer, but let's stick it long because you know we're also just experimenting here with this generator. We'll leave it at long because just in case. I mean, yeah. So long modulus. You'll see where the modulus comes in later. We need a amplifier and an increment. So there we go. And then we are going to first return a result. So random nums equals to num. There we go. It's super simple. And then just like the Fibonacci sequence, a recursive sequence needs a seed start. So we're gonna set the base case to 0. I mean not 0, to seed. And then we're gonna loop through. For I is 1 actually. We're starting from 1. I less than num of nums. And then we're gonna do this this recursive step here. So we're gonna do random nums of I equals amplifier times the random nums of I minus 1 plus the increment amount. Super straightforward, nothing changing. And then we do a modulus here. This is where it's this is where the modulus comes in. It really basically defines this whole generator here, because this is essentially just multiplying by the specified amount plus, and then you can easily reverse engineer this by subtracting the incrementer, and then by dividing by the amplifier, you can get the original number. But with this modulus here, it pretty much scrambles it to the point where sometimes you can get overflows. And that's why, again, I want, later on I'll show you why we want to choose big modulus numbers, not small ones. But then we can just return random nums, and we'll be done with the function here. Down here, let's create a my randoms equals LCG. Alright, let's generate 100 random numbers. And like the seed, I don't really care. You can start with a small c, a big C. I'm gonna spam some numbers here. Actually, I'll start with the small c. I'll start with very bad parameters for this, just to show you how predictable it is if you don't do it right. So, oh, why am I doing it? It should be there we go. And then, what happened? There you go. And then for in or for long, in my RAM nums, we're gonna do system.out.println I. There we go. Alright, so we have 100 random numbers with a starting seed of 3, a modulus of 5, an amplifier of 3, and an increment of 2. Very small numbers, not even in the tens place here, but you can see how predictable this is. So let's run this right over here. And it falls into this pattern here. So we start with 3, 1, 0, 2, 3, 1, 0, 2, 3, 1, 0, 2. Everyone say in the comments, that's right. 3, 1, 0, 2, 3, 1. You get the point. This is very bad because imagine you're implementing this for a game. Now, it lands on a 2. You know it's going to be a 3. So that's bad because we want it to be scrambled. So the key here is to line this in these 3 numbers because the seed, I really don't care where the seed starts. Sure, I mean, you can change the seed up around, but it really isn't going to affect how your RAM number is going to generate. So for my modulus, I actually want it to be a big number such as 2 to the 31st power, and I'm just going to cast this. There we go. And for my amplifier, I'm just going to spam some pretty big numbers because we have this long capability right here. For the increment isn't really as important, but let's just go with some big numbers as well. With these big numbers, we can really scramble up these numbers here. So let's run this again. And you can see, even for these big numbers, it isn't enough to basically scramble these 100 numbers because you can see we fall into this pattern of 10565077742. But in the beginning here, we can get some pretty good numbers here. So we can get this. All of these are pretty random until I don't know how much, like the 20th or the 32nd digit. I'm not going to count that. But we get to up until here, we fall into this basically continuous pattern of 10565077742, and then obviously it's the same for the rest. So that just proves that we can actually further our random numbers here by doing something that isn't really hard coded in, because let's be honest, we can do stuff like private final long modulus equals 1 long distributed by 32. You can make this finals. If these are constants, where will you get the randomness out of it? So we're not going to make these constants, and we're going to make these dynamic variables. And the best dynamic variable that will guarantee you a different number each time is this. That's right, the Unix epoch time. Obviously, with each second ticking by, you're pretty much never going to get that second back. So if we set these to the the Unix time millisecond thing, we'll get some pretty good random numbers. Now we're not gonna set this time to the same, so we can probably bit shift this by, I don't know, like 5 or something. We're just playing around. Increment, let's say the same. Let's see if it falls into a pattern again. But it doesn't look like it to me. I mean, this looks pretty random. And then what we can do is we can set the seed to this as well, and then so that the seed isn't predictable either. But I mean, that looks pretty good to me. And what we can do is we can bit shift this, or we can do some pretty nifty operations with this, and then we can do what else depending on the system things, maybe CPU temperature or something like that. But I'll leave that here. That's just basically generated these random numbers. Obviously very unpredictable. So yeah, I mean, that's pretty much it for this video, you can see this is our seed, which is the Unix time, and then it becomes completely random. I don't think any of these numbers are ever the same. And just like if you ask this, what's the next number? In no way would my human brain comprehend that this number will exist. But yeah, so that's how you basically make your own random numbers. I would suggest using a dynamic variable for these so that you can never get the same numbers again, because otherwise if you hard code these into final constants, you're guaranteed to get some hard code things. So yeah, that is it for today's video. Leave a like, subscribe, do whatever you want with it, and I'll see you in the next one.